Welcome. In this presentation, we see part 5 of topic 3. We would like to take a numerical example to demonstrate or to illustrate the coordinate changes that can give us the minimum number of output differentiators. So if we can recall back from our previous discussion, we want to do some rows and column operation of matrix D so that we can achieve a specific structure where the new matrix D, we call D bar after the transformation, the column and row swapping. It is in this particular form where this submatrix is an invertible matrix and this submatrix is a zero matrix. And in doing so, we would arrive at the least number of output differentiators. And so in this presentation, we like to do it. We like to look at an example. And please accept my apologies for not preparing the slides for this talk. We have the teaching coming up next week, and there are a lot of work to do. So my apologies for that. We'd like to take the numerical example from the book. This is the book itself. By the way, it has 20 chapters. And so far, we've been discussing chapters 2 and 3, and we are up to a numerical example, which is the rows and column operations, so that we can achieve the minimum number of output differentiators. So let's go into the numerical example in this chapter. And so we're going to be nearly there, 20. Yeah, so this numerical example, which is the one that demonstrating the rows and column operation. Okay. My apology. Let's go down. Okay, here is an example. In this example, we just like to show the matrices C and D only. We don't give the matrix A. The whole idea of this example is to show how we can rearrange the columns, the rows of matrix D through the two transformations, which we discussed in our previous presentation. Okay, so we have 5 output measurements. We have 7 stacked variables. We have 4 unknown inputs. And we like to just want to estimate targeted unknown input, which is D1 of T. What would be the minimum number of output measurements, output differentiators that we can use? When we inspect the first 5 rows of this column matrix, we can see that none of them really give us a row equal to 0 at all. So that would mean that we're not able to decompose the unknown input D1 of T in its entirety without decoupling it from the rest of the unknown input. So if we do the worst case scenario, which we discussed in the previous presentation, that would mean that we have to have up to Q output differentiators. That means that we need to use 4 output differentiators for the worst case scenario. And if that is the case, then according to the metric decomposition technique, we pick the metric V where it contains the entire column there. And the metric P has this specific structure. And the metric E has this specific structure because C is in canonical form. We will add it up, be able to decompose the 4 unknown inputs. And if we look at the first row of metric V1, then it has 4 non-zero elements. That would mean that we need to have first derivative of 4 outputs, y1, y2, y3, and y4. This is 1 less than the approach by Howe and Muller. Howe and Muller, if we don't pick this according to a specific structure, in other words, it might end up with a non-zero element in there. So we reduce from 5 output differentiators down to 4. The question is, can we make even lower? So, and that's how we go about doing it in here. We're going to seek to reduce the number of required differentiators by using some coordinate transformation, which we discussed previously. And so let's have a look at this D matrix. To be honest, when I first look at it, it's a bit hard to know how we swap the columns. How do we change the rows, particularly the first 5 rows here? How do we switch the 3 columns here? So we have to just look at it closely and then figure out how to go about doing it. So let's look at the following columns operations. Okay. So in here, what we are telling here is let's swap column 2 of metric D and column 4. So in other words, column 4 becomes column 2 and column 2 becomes column 4. And if that is the case, then the transformation metric Q is given as follow. Well, this column 1 is still the same, but column 4 becomes column 2 here. Column 3 remains the same, but column 2 is swapped into column 4. I hope that makes sense. All right, so what does it mean? Have a look at the following matrix Q, which is basically what is explained in here. So we got this matrix Q. Let's copy that and let's paste that into MATLAB. So we have the following Q matrix. So that basically is telling that column 2 become column 4, column 4 become column 2. And so if we do that operation, we have D times inverse of Q. Now, why inverse of Q? The answer for that is, let's have a look at this operation. So when we say the new vector rearrange, so the old vector is actually the inverse of Q times this new arrangement. That's basically what that is. The good thing about this is that the inverse of Q is actually Q itself. So let's have a look at D times inverse of Q. Then we get this arrangement of the columns. Okay, that's what it is. So we got the column 4. Now move to column 2. Have a look at that. Column 4 was 4, 3, 1, 1, 1, 1, and 0. That's the one. And column 2 in here swap into 4. There. Now, that's just one arrangement regarding swapping the columns. Now, when we do it, something meaningful emerges in here. As you can see, it is highlighted in bold here. 0 and 0 there. And since we are looking for two output differentiators and anything like this happening, that trigger our interest. Okay. So, and remember there are 5 output measurements. So that row in here still belong to the output measurement vector, and the rest of them here, all of them here, belongs to the 5 output measurements. So then what we do next is we're going to arrange the rows. And there are a number of ways in which we can do. As you can see, we can either make this row become number 1. And then we also move this row become number 2, or the other way around. We can move this one to row number 1 and this row to number 2. And then there are many other combinations that we can do. We can basically rearrange them. The ultimate thing that we aim to do is to just put it into this specific structure where that one must be invertible matrix. It's a square invertible matrix. If it's a 2 output differentiator, then it will be a 2 by 2 submatrix and so on. Okay. So now we can see that, wow, there's something that we can do. We can rearrange the number of rows, and there are a number of ways to do it. And so what explained in here is basically the row operations, where what we say in here, let's swap, move row number 3 into row number 1. And let's move row number 5 into number 2. And then the rest of them. So that where equivalently, if we introduce the following matrix M, where M is given by the entries of M is given by all of these entries, then M is given as follow. Okay, let's copy that, put into MATLAB, and we got matrix M. Let's have a look at matrix M. It's just basically just 0 and 1 entries in there. And of course, this is a full rank M matrix. It's just, this is called the coordinate transformation matrix. And if we do that, and then we obtain the new input matrix, we call it D bar. This is the results of 2 transformations. Okay, this is the result of the column, the arrangement of the input vector or non-input vector, and this is about swapping the rows of matrix D. And if we do that, then we got the new matrix we call D bar. We call D bar, and it can be easily obtained. And this is where we got M times D times inverse of Q. And so that gives us the structure that we really want it to be. Okay. So that gives us the structure, and have a look at the structure here. So we get this block here. As you can see, the first 2 rows there is basically what happened in here. And so we achieve that objective of doing the rows and the columns operation, and therefore this will tell us that if in this form we're going to need only two output differentiator, two output differentiators only, and then the new output vector, so basically would be the measurement output number 3 and the measurement output number 5. So the way that's where we rearrange. That's where we rearrange that row, which is number 3, until 1, and row number 5, which is output measurement number 5, into number 2, and therefore we obtain the new arrangement for the output measurement vector. And in order to be able to express the unknown input, d1 of t in its entirety, which will consist of the differentiation of these two, the first derivative of these two output measurements. Okay. And so that's basically the way that we can achieve the minimum number of output differentiators. And when we actually do it, we will get this matrix is the corresponding to the first output the output unknown input. Sorry, it will basically require two output differentiators. So instead of using 4 differentiators, we now only need to use 2. And we take the first derivatives of output y3 and y5. And by the way, the two unknown inputs, when we rearrange them, these new 2 columns here consist of d1, and this column here corresponding to the unknown input d4, the unknown input d4. So when we do the decomposition, we're able to express d1 and d4 in terms of the derivative of 2 output differentiator, y3 and y5. All right. And therefore, if we want to, according to our decomposition, we can also estimate the unknown input d4t as well. And the remaining 2 other columns given in here, they corresponds to the unknown inputs d3 and d2. d3 and d2. Okay. And by the way, we don't need to have the observer matching condition related to these 2 unknown input to be satisfied. And when we look at the new C matrix and we multiply by this one, we can check to see if it's observer matching condition or not. If it's not, it doesn't matter because it's come down to design a linear functional observer for the redo of the system with the 2 unknown inputs, D2 and D3. Okay, so that basically an illustrative example. In this illustrative example, we basically show that we can systematically do the coordinate changes and that can use the minimum number of output differentiators that we can use to estimate a targeted unknown input. And so that concludes the presentation for this topic. And please join me again in the next presentation, where we're going to skip the numerical example because that's just to illustrate the design unknown input. But in the next presentation, which also belong to this section, we're going to apply the estimation of an unknown input in the presence of multiple unknown inputs, and we're going to apply it to an interconnected system. Interconnected system which consists of two subsystems. For the sake of simplicity, it can have more than two subsystems. But what we like to do is we want to design a distributed unknown input observer, one at each subsystem, and at each subsystem, the unknown input observer asymptotically estimate the unknown input vector in that subsystem in the presence of the interconnection of the other unknown input entering the other subsystem. So it's a nice application of what we discussed so far, which is the problem of estimating an unknown input in the presence of multiple unknown inputs. And it can be applied to the design of distributed or decentralized unknown input observers. When we talk about distributed, we also mention referring to the flow of output information from this subsystem. It can flow into the observer for this system, and vice versa. When we're talking about the totally decentralized unknown input, what happens is even though they are dynamically coupled together, but when we actually do the design of the unknown input observer, we only use a local output measurement vector. So that will be discussed in the next presentation, and I hope that you can join me again for the discussion. Thank you very much, and bye for now.